Hi, everyone. Thanks for coming. My name is Mark Hamilton, and I'm a software engineer at Microsoft. And today, we'll be exploring how we can effectively pull knowledge straight out of the internet and create our own object detection models without actually needing to label anything ourselves. And if you saw today's keynote demo in Rohan's talk, where we effectively used Bing on Spark to create a huge labeled data set, we'll effectively be doing a similar scenario, but pushing that even further and refining that with some new mathematical techniques. But first, I want to actually introduce the application that we've applied this technology to. So recently, we've partnered with the Snow Leopard Trust, a small nonprofit who aims to monitor and protect the endangered snow leopard population. And they're based out of Seattle in Kyrgyzstan. One of the things you might have seen on your Facebook feeds or across the internet is that snow leopards are no longer considered endangered. And that was a big celebration across the world. However, this kind of doesn't, it's not all that great when you come to think about it. And technically, the Snow Leopard Trust actually opposes this decision. And one of the reasons they oppose it is it's not like any new snow leopards were found out there in the wild. Really just a parameter changed in some statistical model that someone used back in the day, and now there's like slightly more snow leopards according to that model. So nothing actually physically changed in the world for them to change this classification. And so to the scientists, what that means is like maybe we don't understand our models correctly if they can sway that large. And so technically, you should be really sure about the population of snow leopards before you ever take them off the endangered species list, because the snow leopards being removed from the endangered species list means a whole lot of protections that go along with that get removed as well. So the Snow Leopard Trust is really aimed to get a better handle on how many leopards are left and whether their population is increasing or decreasing, and has actually created like large worldwide collaborations between snow leopard research labs to try to pool data to make this possible. And so some of the reason why it's so hard is that if you look at potential snow leopard territory, it's spread out across 1.5 million square kilometers. And these aren't the easy 1.5 million square kilometers. These are the really hard 1.5 million square kilometers. Like we went there and we couldn't even get to a single snow leopard location where they put these camera traps that we'll talk about later. It's like this crazy mountainous terrain that's really far up there, not paved at all. And snow leopards, there's only about 4,000 of them spread out across this. So that's like one snow leopard per hundreds of thousands of square miles. So it's ridiculous how diffuse the leopard population is throughout. So they're incredibly difficult to study. And you can really only study them in two ways. One, by trying to trap them and collar them. And that's incredibly difficult because they're so rare. The Snow Leopard Trust has done that for 10 years, and they've maybe trapped and collared 20 leopards over the course of 10 years. And the other way is through remote camera trapping. And so this is what the Snow Leopard Trust has mainly employed. And over their 10-year existence, they've taken about 1.3 million images across a variety of sites. And some of these images are great photos of snow leopards, but the majority of them are just goats. They have this huge data set of goats and grass and random other things that aren't snow leopardy at all. And furthermore, it's also very difficult to tell what is a snow leopard and what's not. Like this is a particular example from their data set. And as you can see, it's very hard to actually find this kind of leopard in this image. So it really necessitates an algorithmic solution. And so the way we go about solving this problem is through a technique called deep learning. And I'm sure you all are very familiar with it these days. But for those who aren't, it's the idea of we want to create algorithms that mirror the structure of the human brain as closely as possible. And they've recently become a favorite because they're really fast. They're quick to train. They have an amazing performance because they train the entire architecture front to end using a technique called stochastic gradient descent. And furthermore, for academics, there's a large space of models. So you can do crazy things with deep networks because you don't actually need to worry about fitting them. There's software out there like TensorFlow and CNTK and PyTorch. Once you build the model, it takes care of fitting it for you. So you don't need to do a lot of thinking. It's very easy to make models, so it's very quick to publish least publishable units and get your name out in print. And so what we use is a technique called deep transfer learning. And the basic idea is that we take a network that already knows how to see quite like a human being. It's been looking at ImageNet, this million image corpus of things from around the world, like cats and dogs and apples and oranges. And so we don't need to do all that much to turn it into an expert vision network. We kind of take this complex network, and we cut off a few layers, and we put our own models on the end of them to kind of learn to become Snow Leopard specific classifiers as opposed to very general purpose classifiers. And the way we do that is by using SparkML. And so SparkML is one of the core technologies that we use for this, and it's basically a high-level library for distributed machine learning. If you've used scikit-learn, which is its non-parallel cousin, it's got a very similar look and feel to that, in that every single thing in the machine learning ecosystem has the same API, which means that you can easily swap out one model for another. You could start off with linear regression and then soup it up with something more complex when you're ready for it. And so what we aimed to do in this project was to combine the benefits of deep learning with some of the benefits of distributed computing. And more specifically, what we did in this project is that we took the deep learning framework, CNTK, and we combined it with Spark so that you can now evaluate these deep networks that you train with Microsoft CNTK on Apache Spark using the full parallelism of your cluster. And we did this in the same API of SparkML. So if you guys have used the Databricks version, which is the TensorFlow on Spark, it's very similar, but for another automatic differentiation framework. And so we released this back in the day, actually on the same exact day as Databricks. So it was like, whoa, that's kind of converging of thoughts. And so we released this into an open source library that we call Microsoft ML for Apache Spark. And it combines, it's kind of where a lot of initiatives at Microsoft to take work and move them all into the Spark ecosystem live. And so it's an open source library, and it works in Python, Java, and Scala, wherever you get your Spark. And the goal is to kind of create systems and integrate machine learning components so that they work in the batch, streaming, and serving environments. They work no matter what kind of cluster you have, be it a Databricks cluster or maybe your own cluster on premises. And it works independent of whether you're on a single node or whether you're using dynamic allocation or serverless. And so part of the pieces of MMLSpark is we'll talk a bit about today about CNTK on Spark that's integrating deep learning in Spark. We also have a new announcement today where we have created a serving framework built on top of Spark that takes any Spark computation and turns it into a distributed web service. We'll go into that a bit. And in the past, we've released HTTP on Spark. This is an integration between Spark and the entire HTTP protocol. And so what that means is that any web service that you ever create, anything that communicates via the standard networking protocols, you can embed into your Spark computations and leverage in a parallel fashion. And so we build on that to release the cognitive services on Spark, which we'll talk a little bit about later. And so one of the benefits of being able to put everything in this nice SparkML API is that the code, when you actually go about writing it for your production use case, becomes really slick and very simple. And so this is an example of the code that we use for the deep transfer learning example. You see we basically pull down a deep learning model. We augment our data set a little bit. We pass it through a deep image featurizer and then throw on a logistic regression on top. And then we can split a data set, fit, and train our model. And so it's very simple. It's only like 14 lines of code to do something seemingly very complex, which is train a deep transfer learning model on a new set of data. And what we find when we use this approach is that out of the box, it yields a really nice boost in accuracy, going from something like 65% to 95%, which is a big boost for something like this kind of Snow Leopard recognition system, because that means you can really trust it a lot more. And more importantly, it means that we have less false negatives, which are basically leopards that slip through the cracks. And those are very important use cases, because if we have too many false positives, or goats that are identified as leopards, we can very easily cull them out because it's a small population of leopards. But if you have too many false negatives, those slip back into the 1.3 million images that we can't identify. So that's really the case we want to avoid. So now that we have like a trained leopard classifier, we can go ahead and move it into production. And so our first work on this was kind of integrating Spark and Power BI, this kind of rich visual language tool that you can use to understand and visualize your data. So we've done this with Spark Streaming. We have a Spark Streaming pipeline that pulls data from Kafka that's kind of collected from all these cameras in parallel, pushes it through our deep network, and finally writes it out to Power BI. And we can take a look at the results. we've used this to create kind of a real-time Snow Leopard monitoring system that the trust can use. And so we can actually come in here and take a look at each individual survey. I'll come to some of the more later ones here. And we can connect these classification sets with the actual GPS coordinates of the camera and the photos they take. So we can scroll through these different Snow Leopard photos and see like what's actually going on at these different sites. We can kind of see which sites are the most important. And this takes a little while to load, but in maybe a few seconds it'll pop up the leopards that show up on that particular site. And one of them that I really want to point out is this latest one, Shamshi 2018. And so it'll take a little bit while to load. But so this site is very important because it really just recently came in. And one of the exciting things is that this is a brand new site that the Snow Leopard Trust investigated. And this was kind of a pilot test to see are there any snow leopards in the region. And when this thing finally loads, we'll see that there was indeed like a snow leopard found, and it was kind of very exciting news, which means that they're going to scale out their monitoring efforts in Shamshi. And so this is where we actually tried to get when we visited Kyrgyzstan, and it's really, really hard to get to because it's very, tucked into this huge mountain range, and the road basically ends here. So it took a very long time to get to this one particular camera, but they're planning to scale it out to see if this is a region that's kind of worth protecting with a larger protection apparatus. And so one of the things that we've done in our work is we tried to make it as simple as possible to actually perform this analysis. And so to take our trained model and to actually write it out to Power BI, the code basically looked like this. It was a 3-liner where we take, we read a stream from either Blob or you can use Kafka or something like this. We take that data frame, we transform it with our fit model that we learned earlier, and then we take these results and we stream them out to Power BI, and Power BI lets you just send it a URL. And so with those 3 lines, you can kind of create like a real-time distributed fault-tolerant Leopard processing system, and it gets great throughput, and it's near real-time. So we're talking like maybe 1 to 2 seconds of latency. But if you really want to create something that's like real-time and responsive and doesn't need a Kafka cluster to work, then what you really want is a web service, something where you can just send it a piece of data and get back the response immediately. And so for that, we've created the Spark serving engine that kind of tries to unify streaming batch with another kind of mode of operation, namely serving. And so the idea is that serving on a Spark cluster is not too different than streaming on a Spark cluster. In streaming, you have a point A and B, and you push data through a pipeline continuously. Whereas serving, your point A and B are kind of the same thing. You get data from a web request, you process it, and then you send it back on that same exact web request. So the serving can be very easily built on top of Spark streaming, and that's what we've provided here with Spark serving. And so what we've more specifically done is that we've built it on top of Spark continuous streaming rather. And this is the new announcement that was made maybe last Spark Summit, where all of the Spark pipelines can kind of be souped up to have sub-millisecond latencies. And so because we build on this, we also get sub-millisecond latencies. And it has the same API as the batch workload. So it's very easy to hook into. You just need to kind of load your data frame in a different way. And so one thing I forgot to mention is that we announced today in the keynote that we're contributing this back to the open source. And so we've opened up a Jira, and you guys can all check it out if you want to see what's under the hood, and also if you have any API suggestions, because we want to make this something that the entire community can use and benefit from. And so this is kind of the API, and again, the goal is to make this as simple as possible. So the kind of APIs that we come over here, instead of saying spark.read.csv, we can say something like spark.readstream.server. And that says we want to create a big distributed web service where each server has this host, this port, and this path for the API. And then when we say .load, we effectively have a data frame that we can manipulate using all of the standard Spark operations that you know and love. And in this case, we can fit a model to it and transform it. And then finally, we have these transformed results. That's the probabilities that our model will output. And we can just write back to the original stream, the leopard detector address, and then start that query. And so that creates a distributed web service in like 1 second, basically. So it spins up incredibly quickly because there's no need to export anything. If any of you guys have used MLeap, you know that there's like this whole exporting process, and then you got to spin up another machine to serve it. But it doesn't really make any sense because you have a big distributed cluster already, namely Spark. So why do you need to change that? You can just leverage that architecture, save yourself a lot of time and headaches. So the basic idea is that on each node, we spin up servers and manage them for you. And then you can tie these servers together with a load balancer so that when a user sends its request up, it'll randomly pick one of the Spark executors to send it to, and so that you can parallelize your web requests. And so up until this point, we've talked about a standard machine learning scenario, basically supervised classification, where we have a data set that the Snow Leopard Trust has made for us, where some of them are leopards, some of them are not leopards, and we learn a computer vision algorithm to distinguish between the two sets. But here's where we kind of push the envelope and go a bit further than that, because we don't actually need the Snow Leopard Trust to provide a labeled data set. We already have access to something to generate a labeled data set for us. And the basic idea is that the internet has been logging our whole human experience for as long as it's been around. And it contains a huge amount of structured knowledge. And search engines have been capturing this knowledge and using it to provide an interesting experience for us. Like for instance, search engines kind of pull knowledge not just from the state-of-the-art machine learning algorithms that they employ, but also through clickstream data and the fact that people upload captioned photos and a huge variety of different avenues. And they condense this knowledge into a way that helps us explore the world. You know, whatever you're interested in searching for, you can type it in and immediately get thousands and thousands of results. And so this kind of technology not only helps us learn, but we can also use it to help our algorithms learn. And so the basic idea is that we just need to search for snow leopards, and we immediately get basically a limitless list of snow leopard photos that goes on for eons. And we can use Spark to effectively pull all of this data straight onto the cluster to create a full large collection of snow leopard images without us having to actually do anything. And you might ask, now we have these snow leopard images, what do we compare them against? And what we'll compare them against is effectively random queries. And so Bing Search doesn't have a random image API, but we can kind of approximate this by searching for random words, which are very easy to generate. We just Googled for random word generator, and we found a website and generated like 30,000 words and slammed Bing with them. And so now we have these two data sets, one of snow leopards and one of random other natural images. And so by creating a classifier, that classifier needs to know like what to pick out to actually determine whether an image is from that snow leopard query or from any one of the other random queries. And so now we have this full data set, and we can proceed with the earlier analysis. It's a supervised problem now. We can just pipe it through the deep network, append it with a logistic regression, and find that we still get really good accuracies. And part of the effort in this work is to make this as easy as possible. And so this is what the actual API looks like. And it's designed to be identical to any other SparkML model that you might work with, like logistic regression or string tokenization or anything, but instead you're calling Bing in a large distributed web query. So for instance, to create the leopard side of the data set, we create a Bing image search object, we set the subscription key, we can set a column of offsets. This helps us page into Bing to get the first like 100 pages or something. We can set a column of queries. This will basically parameterize the web calls we make and say, I want to get a snow leopard for every single offset into the data frame. And we can even set things like the count, the number of images to return, the image type. We can do filtering right here in the API. So you can say, I just want photos, I just want line drawings. Or if you're worried about getting sued, you might just want public images or images with certain licenses. And the Bing API naturally supports that. And so this is kind of part of a larger push to make every single one of the cognitive services really easy to use in a distributed fashion on Spark. So today, in the keynote as well, we announced an integration between all of the cognitive services in Spark, and we've started by making really nice and easy to use distributed cognitive service bindings for Bing, the text analytics services, the computer vision services, and the face APIs. So this will allow you to embed like much more complicated pre-built AI models straight into your SparkML pipelines and not worry about it. And so one of the ways that we've used this in other demos is that you can now take cognitive services and chain them together to do what you want. So we have an example up on our website where we take Bing image search and combine it with vision services and text services to make like a celebrity quote analyzing dashboard. So you can like take a look at all the sorts of motivational quotes out there and see who's saying what and who's most negative and who's most positive. So spoiler alert, Drake is the most negative. He's very whiny. So he's high up there. And what this is basically leveraging is a technology that we call HTTP on Spark, which I touched a little bit about earlier. And what this is a fundamental integration between the entire HTTP protocol and the Spark SQL database schema. And so this means that we have like a type in Spark SQL that mirrors everything you could possibly want in an HTTP object, like headers and bodies and all sorts of things like this. So it effectively allows us to integrate anything we want into Spark that communicates with HTTP. And some of those being the cognitive services, but if you have your own service, you can also integrate it into your SparkML pipelines, and it kind of looks like this, where you'd basically set the URL of your service and then say what kinds of data you want to send to it. And so this is kind of the other side of the networking stack. We've created distributed web services on a Spark cluster, and now this is distributed web clients on a Spark cluster, so kind of completing the web interface of Spark, so to speak. So now that we've been able to find a way to effectively pull labeled images straight out of Bing to create our own classifier, we want to take this and go even further. What if we want to get something like an object detector, something that actually detects the pixels of the image that we care about? And so for that, we can use a mathematical technique called LIME. And LIME is a pretty cool technique because it effectively takes any classification algorithm that you have and lets you understand what it's doing underneath the hood. So this is an example from the LIME paper. And they took this kind of dog playing a guitar, and the top few classes it spits out are acoustic guitar, electric guitar, and Labrador, because I guess that's what this image is a dog playing the guitar. And so you can ask the network, like, why did you spit out a guitar? And the pixels that it will return, saying that the pixels that really explain why it spit out a guitar will be exactly the pixels that you're thinking of that would explain a guitar. And then you can ask it, why did you spit out a dog? And it will kind of highlight the pixels that are most dog-like in the image. And the way this actually works is by taking an image, breaking it up into its kind of big chunks, and then randomly turning these chunks on and off. And so if we turn a specific chunk off and suddenly what we're looking at is no longer a dog, then you can kind of infer that that chunk is a dog-related chunk. And if we take one of these chunks and randomly turn it off and nothing really changes, then you know that that chunk isn't really as relevant. And so what this allows us to do is when we have a classification algorithm, without knowing what the classification algorithm is doing under its hood, we can just feed it examples with chunks turned on and off. And eventually, when we feed it enough examples, we can get a good picture about what's important for the classifier. So, this classifier doesn't need to be some kind of algorithm. It could even be like your grandma sitting, answering questions about images, and you'd still be able to pull an explanation out of this that effectively highlights the pixels that you care about. So one of the announcements that we have for today is that we've integrated this kind of mathematical technique with Spark so that you can do this for any SparkML model that you have that works on images. And the idea is that LIME, this technique, requires generating thousands and thousands of perturbed images and feeding it to your deep network. And that's incredibly costly. It kind of magnifies the time of computation by 1,000. And so if it took you an hour to process all of your data, if you just naively applied a LIME to it, it would take you 50 days to actually interpret all of your data to get kind of more refined predictions. But our method is parallelized using the full parallelism of the cluster. So it aims to really cut down on the amount of time actually needed to create these kinds of interpretations. And so what's important about this method is that, let's say we interpret a Snow Leopard classifier, what it will spit out is it will highlight kind of the exact pixels where the Snow Leopard is. And so this is a much more refined output than just a yes or a no. That from this, we can now know where the leopard is. And more specifically, we can actually just draw a bounding box around that LIME output. And this will kind of track the leopard as it moves through the space. And so what we now have is a way to, from just the classification system, refine that classification system into an object detector, something that does a lot more than just classification. But the cost is that you got to effectively evaluate your network 1,000 times every time you want to figure out what the bounding boxes are. So you gain this huge computational cost associated with it. So that's kind of where the next part of our work leads, which is we have this method to turn a classifier into an object detector. And it's for free. We can do it with anything we want. But it's so costly. Like, how do we take the knowledge that this LIME method learns and distill it into a form that's much faster for us to use? And so for this, we actually take these bounding boxes that we painstakingly compute with LIME, and we treat those as supervised labels that we can then use to train an object detector, in our case, faster RCNN. And so what we get is that the outputs of this kind of whole pipeline of training a classifier using images from Bing, interpreting that classifier with LIME, drawing bounding boxes around the interpretations, and then training an object detector to replicate those bounding boxes really closely matches with that of human labels. That we effectively get full human labeled data set, something that can automatically generate bounding boxes, but we never used any human labeling throughout the process. We got the classification data from Bing, we generated the object detection bounding boxes ourselves. So it's effectively a way to just pull an object detector straight out of Bing for whatever query you want to search for. And so some also, I should definitely mention some limitations of this, in that in our first attempts at this kind of work, we found that it made a few systematic kinds of errors, where, for instance, in this photo over here, with a human would recognize that this is actually two leopards walking in a scene. However, our algorithm only detects one of them. And this is because we just use a very naive way of creating bounding boxes. We just take the LIME outputs and we slap one bounding box around the output. And so this won't do very good if we're trying to find two leopards, or if there's two regions of the image that explain the model's classifications. And so to tackle that, you can potentially cluster the LIME outputs or something more complex. And then also, we find that it still performs poorly on images that are incredibly difficult to spot for the human eye, like this one over here. And we believe that this is because of an anthropic effect, where if you think about the images on Bing, these are going to be platonic snow leopards. They are going to be the ideal, perfect snow leopards that you see in the zoo and things like that. They are not going to be super camouflaged leopards hiding in the brush, because that's just not what Bing returns. And so your algorithm will suffer when it kind of goes out of sample in this kind of systematic way. And so that's kind of something we found as well. And so I know that that was a lot of information, but to recap on the full kind of architecture that we've used for this analysis, we pull our data directly from Bing image search, and we can effectively generate a labeled data set with this. We stitch them together with Spark SQL, pass them through a deep network, train a SparkML logistic regressor to learn a classification algorithm. Then we pass it through distributed model interpretability on Spark, draw some bounding boxes around the outputs, and finally, we trained a deep network to reproduce those bounding boxes. And you might ask, like, why is it so important that we actually get these bounding boxes around the snow leopards? And part of the reason is that when you have a classification system, you just know whether or not a leopard's in the image. You don't know whether that leopard is leopard number 395 who's been walking around or not. And this is really important for actually understanding how many leopards there are in the wild, because we don't know if there's one really selfie-happy leopard, or whether there's 1,000 shy leopards out there. And so to be able to understand whether the actual population of leopards, we need to actually create like a leopard database. And the idea is that the spot patterns on these leopards are kind of like human fingerprints. They uniquely identify the leopards. And so we can use a tool called Hotspotter to actually take these different object-detected leopards and compare their spot patterns. But in order to use this tool, we actually need bounding boxes around the individual leopards. It can't just work on an entire image. And so the goal is to really automate the whole pipeline of leopard conservation, where we go from detection to individual leopard linking, and then finally we pass these into these models that actually determine how many leopards there are in the world to finally answer the question of are leopards truly endangered or not, and how much resources should we devote to their protection. So in conclusion, we have a couple big releases in this cycle. We've released the cognitive services on Spark, sub-millisecond latency distributed web services, and distributed model interpretability in SparkML. And we aim to kind of give all this back, so all of this is open source. We're adding Spark serving into Spark core, and you can check out the code at aka.ms/spark, and you can feel free to contribute or reach out to me or the team. And thank you all for listening, and thanks for the team who kind of created this, namely the Microsoft AI Development Acceleration Program, who's been working on this as their project.